Section: Introduction. In this section, we explore how high-energy physics, HEP, has increasingly adopted machine learning, ML, techniques to address various challenges like event reconstruction and anomaly detection. We notice that the growth in model sizes and the popularity of transformer-based neural networks in ML have not yet been fully embraced in HEP, particularly regarding foundation models, FMs. These are large pre-trained models that can be fine-tuned for specific tasks, commonly used in natural language processing, NLP, and computer vision, CV. FMs undergo a pre-training phase where they learn from a vast amount of domain-related data without needing labeled examples. After this, they can be fine-tuned for specific tasks using labeled data. In NLP, for instance, pre-training tasks might involve predicting the next word in a sentence or filling in missing words, while downstream tasks could include sentiment analysis or translation. The FM serves as the backbone for these tasks, holding most of the model's parameters. We find that the self-supervised learning (SSL) approach is particularly beneficial for HEP since experimental data often lacks labels. Many HEP tasks rely on simulated datasets, which can be time-consuming to create and may not perfectly represent real data, leading to discrepancies when applying models trained on simulations to actual data. This motivates us to develop SSL techniques that can work directly with real data. In our work, we build on a previous SSL strategy designed for unordered sets of particles, which are reconstructed from signals captured during high-energy collisions, like those at the Large Hadron Collider, LHC. Each particle has various attributes, such as energy, momentum, and type. Our method, called MPM, involves masking a random subset of these particles and training the model to reconstruct them. This is similar to masked language modeling but adapted for unordered particle sets. We also consider the concept of denoising autoencoders, where we apply a corruption method to the input data and then train the model to recover the original signals. Masking is a straightforward and effective way to corrupt data, making it applicable across various fields. In our study, we focus on particle jets, which are sprays of particles produced during collisions. We treat each jet as a complete set, and their structure is influenced by the type of particles involved. MPM serves as a method for training an FM that can be fine-tuned for supervised tasks related to jet studies. Since most particle features are continuous, we cannot directly apply the same training strategies used for language models. Instead, we draw inspiration from image processing techniques, using a vector-quantized variational autoencoder, VQVAE, to create tokenized representations of particles. This shifts our reconstruction task from regression to classification, allowing the model to predict the codebook ID of each tokenized particle. We argue that using VQVAE-derived targets during pre-training leads to better performance because the VQVAE's latent space contains rich semantic information, and the classification approach teaches the model a more expressive distribution. However, training the VQVAE adds complexity and can lead to information loss. In this paper, we present our contributions. 1. An improved MPM training paradigm, MPM v2, which enhances the model architecture and expands particle attributes. 2. A study of alternative reconstruction tasks for MPM v2 that eliminate the need for VQVAE targets. And 3. A new testbed for pre-trained models that includes a broader range of downstream tasks relevant to jet physics. Section Summary. In this section, we discuss the integration of machine learning in high-energy physics, particularly the development of foundation models, FMs, for tasks like particle reconstruction. We introduce our improved masked particle modeling approach, MPM v2, which enhances model architecture and explores alternative reconstruction tasks to streamline training without relying on the complex VQVAE process. Section: Related work. In this section, we discuss related work in the development of foundation models for physics, alongside our MPM approach. One of the early efforts utilized the SIM-CLR framework to pre-train a fixed encoder, applying physically inspired augmentations like rotating jet constituents and smearing soft constituents to estimate soft radiation. The SIM-CLR framework was also employed in ray simulation-based self-supervised learning, which relies on simulated data where each positive pair comes from the same event but is altered by different simulation settings. Another recent work, OmniJet Alpha, adopts a method similar to MPM but focuses on predicting the next token instead of masked reconstruction. Like MPM, it masks only the particle type while keeping kinematic features available. We also note that some studies propose using elements of the reconstruction pipeline as pre-training tasks. The OmniLearn model combines supervised classification for jets with a diffusion generative model. Regarding our data, a significant feature of MPM is its ability to work without labels, allowing direct application to experimental data. However, due to the lack of large open datasets of real jets, we rely on Monte Carlo simulations for framework refinement. Importantly, we do not use truth labels during pre-training, and our conclusions are based solely on models trained on the same datasets. Access to truth labels helps us evaluate the performance of our foundation models. We focus on two datasets generated using the Delphi's simulation package. The first dataset is publicly available and contains 120 million large radius jets across 10 classes, each representing different physical processes. The second dataset, labeled BTAG, includes 3 million jets from 3 classes based on the quark flavor that initiated the jet: light, charm, or bottom. Both datasets use the anti-KT algorithm for jet reconstruction, with different radius parameters. The jets in the first dataset have higher transverse momentum, while BTAG jets have a lower threshold. Additionally, the first dataset includes both charged and neutral constituents, while BTAG only has charged particles, leading to differences in the average number of constituents per jet. We use the first dataset for pre-training our models and fine-tune and evaluate using both datasets. The variations between these datasets reflect realistic differences in how particle physics jets are defined in various experimental contexts. These differences provide an opportunity to assess the generalizability of our model to new tasks and out-of-distribution datasets. In our approach, each massless constituent is represented by its kinematic properties relative to the jet axis. We expand this representation to include common attributes used in experiments, such as impact parameters for charged constituents and zero padding for neutral particles. This results in a set of continuous features and a one-hot encoded vector for particle identity, forming a comprehensive representation of each jet. In MPMV1, we select a subset of particles from the jet and replace their features with a special masked token, aiming to recover those features. We treat the input sample, its latent projection, and the decoder output as sets, ensuring that all mappings between them are permutation equivariant, which means we do not use positional encoding. The corrupted sample consists of the remaining particles and the masked tokens. We employ a transformer as the encoder and a multilayer perceptron as the decoder. For MPMV2, we propose several modifications. We found that removing masked tokens from the input set and reintroducing them only during decoding improves efficiency. This adjustment leads to a model that resembles a more traditional approach. We also expanded the decoder to a full transformer, which yielded better results. However, we found that providing too much positional information in the latent space could trivialize the reconstruction task, so we limited positional encoding to the masked elements only. The loss function is then derived by comparing the original and reconstructed samples across various tasks. Section Summary. In this section, we review various foundational models for physics, highlighting approaches like SIM-CLR and OmniJet Alpha, which utilize different pre-training strategies for jet reconstruction. We also discuss our use of Monte Carlo simulations for pre-training MPM, focusing on two datasets that illustrate the variability in jet definitions and features, ultimately emphasizing the model's ability to generalize across different experimental settings. Section: Reconstruction Tasks. In this section, we explore reconstruction tasks. Unlike MPMV1, which only used a VQVAE-derived task, we now combine multiple tasks to separately recover continuous and categorical features. Each task requires additional learnable layers, known as task heads, and contributes a loss term that we sum for our combined pre-training. We examine 5 different reconstruction tasks for continuous features and 1 for categorical features. For particle identification, our first task is to identify the particle type of the dropped constituents, which is a standard classification problem. We employ a linear layer and use the cross-entropy loss function for this task. Next, we include VQVAE tokenized classification, which is part of the original MPM approach. Here, we first train a VQVAE to embed the jet using only continuous features, mapping them to indices in a learned codebook of size 1024 with a vector dimension of 32. Again, we use a linear layer and the cross-entropy loss function. In direct regression, we revisit this method, which we previously found insufficient for pre-training, but we believe it may yield better results with our more powerful decoder. We use a linear layer and apply L1 loss to recover the continuous features of the particles. For k-means tokenized classification, we test a simpler token reconstruction task using k-means centroids. We fit k-means using the continuous features and the first million jets, finding that 16,384 centroids is optimal. This fitting process is quicker than training the VQVAE, and we also use a linear layer and cross-entropy loss here. In our conditional normalizing flow task, we aim to learn the full posterior distribution without the information loss from discretization. We implement a conditional normalizing flow model with 6 coupling blocks and a Gaussian-based distribution. Each block uses a 2-layer MLP to output spline parameters based on half the features and context information, maximizing the log likelihood of the transformation. Lastly, we explore conditional flow matching, a recent approach in diffusion-based generative models. We follow the CFM framework, where a model learns the probability vector field connecting data and noise distributions over time. Instead of directly constructing the probability density function, we approximate the velocity vector using a neural network. We derive our training objective from the continuous features of a particle and the corresponding decoder output. We sample a diffusion time and mix noise with the original features to create a target for the model, which we approximate using a 3-layer MLP. Section Summary. In this section, we explore various reconstruction tasks to recover continuous and categorical features, employing multiple learnable layers and loss terms for combined pre-training. We investigate 5 tasks for continuous features, including particle identification and conditional normalizing flow, alongside a classification task for categorical features, aiming to enhance the model's ability to learn and represent complex data distributions. Section: Set-to-set flow matching. In this section, we explore a set-to-set flow matching model, or SSFM. This model employs a time-dependent transformer decoder to create a complete set of components based on a set of latent nodes. It resembles the diffusion masked autoencoder from computer vision. Similar to our previous model, MPM, we divide the input set into a smaller set and its complement. We pass the smaller set through an encoder to obtain a latent set, which is then utilized in the decoder's cross-attention layers. The decoder is trained as a set CFM model to generate the remaining components. A diagram illustrating this model can be found in the referenced figure. Since the loss function focuses solely on denoising the complement set, we do not face issues of degeneracy, and there is no need for positional encoding or mask tokens. By adjusting the masking rate, which is the ratio of the smaller set size to the total set size, we can control the amount of data generated by the diffusion model. When the masking rate is 0, the decoder functions as a standard diffusion generator. Our pre-training setup establishes a foundation for embedding and a purely generative model for the components, similar to OmniLearn and OmniJet Alpha. During training, we sample the masking rate to balance our objectives. For our ablation studies, we assess the modifications made to MPMV1 by using the new backbone as a fixed encoder for classifying the dataset. After pre-training for 200,000 steps, we freeze the encoder and add a classifier head, which consists of two class attention layers followed by a linear layer. We then train this head as a classifier using cross-entropy loss for another 200,000 steps. We focused on regression, k-means, and particle ID tasks for the ablation study due to their quick prototyping. The complete results, including all reconstruction tasks, are detailed in another section. We present the ablation study results in a table. Initially, we replicated the training setup with a masking rate of 0.3. Next, we tested the setup with updated transformer layers. We then incorporated impact parameters into the particle features and added particle ID inputs along with the ID reconstruction task. Each of these modifications enhanced the classification accuracy of both models. The most significant improvement came from switching the decoder to a transformer, which reduced the accuracy gap between the two methods from 10.5% to 2.2%. To confirm the effect of this change, we reran the regression task without the impact parameters or particle ID task, achieving an accuracy of 65.0%, an increase of 9.5%. Another advantage of adopting the May setup was a 40% reduction in GPU memory usage due to the smaller point cloud size sent to the encoder. We also experimented with adding a feature to the encoder that prevents the transformer from overriding elements in the set with global information. After adding this feature during training, we observed an improvement in classifier performance with minimal computational cost. Additionally, we optimized the masking rate and decoder depth for our final training sessions. In the downstream tasks, we evaluate the performance of our backbones on various tasks commonly encountered in jet physics. Each backbone undergoes pre-training using one of the continuous feature reconstruction tasks, along with the particle ID task, for 1 million steps. After pre-training, we append specific layers for downstream tasks to the encoder and fine-tune the model for 200,000 steps, allowing for early stopping based on a validation set. We use a randomly initialized network as a baseline to demonstrate the benefits of pre-training and repeat each experiment 5 times to assess variability. For in-distribution classification, we use the same classifier head described earlier. We measure the backbone's data efficiency by varying the number of jets used for training the classifier from 1,000 to 100 million, with results displayed in a figure. At each training size, all pre-trained backbones outperform the randomly initialized network, although this advantage decreases as the number of jets increases. At the maximum of 100 million jets, all backbones achieve an accuracy between 85.0% and 85.3%, while the random initialization reaches 84.3%. Notably, the k-means backbone performs best with larger datasets, while the CNF and regression backbones demonstrate greater data efficiency. The flow backbone matches the performance of the randomly initialized network with 1 million jets when trained with just 10,000 jets. Section Summary. In this section, we introduce a set-to-set flow matching model, SSFM, that utilizes a time-dependent transformer decoder to generate a complete set of constituents from latent nodes, while also detailing our ablation studies that demonstrate significant improvements in classification accuracy through various modifications, particularly by switching to a transformer decoder. We further evaluate the performance of our pre-trained backbones on downstream tasks, showing that they consistently outperform randomly initialized networks, especially in data-efficient scenarios. Section: Weakly Supervised Classification. In this section, we explore weakly supervised classification. In many experiments, we cannot create perfectly labeled data, so we focus on how our model performs when the labels are noisy or incomplete. The concept of classification without labels, or CWOLA, suggests that the best classifier for two mixed datasets with different signal and background ratios is the same as the best classifier for two pure datasets. We apply this idea in template-based anomaly detection and muon isolation. To simulate the CWOLA scenario, we use two datasets of 500,000 QCD jets, injecting top-initiated jets into one as our signal. We employ the same classifier head as in our earlier experiments. We present the significance improvement, SIC, from applying the classifiers on a test set with pure QCD background and top signal samples. We define SIC as the signal efficiency, or true positive rate, divided by the square root of the background efficiency, or false positive rate, at a 99% background rejection level. Our pre-trained backbones significantly outperform the benchmark, with the regression backbone achieving the highest performance when only 500 top jets are included in the training set, resulting in a SIC of 8.18. Next, we assess the performance of our backbones in classifying the B-tag dataset, which features lower energy, narrower jets with fewer charged particles. We show the accuracy of our three-class classifier based on the number of jets used for training. All pre-trained backbones exceed the benchmark initialization, demonstrating that the learned mappings are applicable beyond the initial dataset. In this task, the CNF backbone performs the best, but all pre-trained backbones reach around 70% accuracy when using the maximum number of jets.